It's my pleasure to introduce our next speaker, Jeff Mather, who is a senior software engineer and development manager for image processing toolbox at MathWorks, which makes MATLAB, which is in common use throughout many scientific disciplines. He's managed that team since 2013, and he's been with MATLAB since 1998. So his areas are file formats, which this kind of works in very well with the previous talk. Image processing, high dynamic range imaging, color science, and optimization of software performance. He graduated with his undergraduate degree in mathematics from Grinnell and has a master's in engineering from Brandeis University. Today, he'll talk about the challenges of processing very large pathology images and presenting a framework with which to solve problems in segmentation, feature extraction, measurement, and labeling. Without any further ado, Jeff Mather.
Hi, thank you. All right, so I'm really happy to be here today talking with you all about the challenges and novel solution that we've come up with, my colleague and I, and I'm going to present for the both of us. All right. So I'll talk about what some of the goals and challenges in this space are, and then I'll provide the possible set of solutions and the framework that we ourselves have come up with. And at the end, I'll show an example of how this can be applied for semantic segmentation of whole slide images. All right, so the high-level goals are probably not a surprise for people in the area, but for everyone else, it's essentially how do you assess the health of tissue on a slide. This is one of the main things that's done in digital pathology in order to identify disease, to classify the state of disease, and then also to evaluate how well a drug is working. Sometimes you want to know what's wrong with a person, and sometimes you want to know, is the solution actually working and making it better? Does it make a tumor shrink? Does it make it grow? Does vascular change over time? What happens to cell division, and so on? You see here on the left-hand side, a typical whole slide image showing a section of tissue, and then zoomed in, you see some more nuclear detail. Below that is a segmentation of those tissues and cell parts into their different constituents. And some of the questions that people may want to have answered are related to counting, morphology, classification, and overall statistics about an image. And then also segmentation of images into different classes of things. Tissue, is it necrotic? Is it a tumor? Is it healthy tissue? Or is it none of the above? Is it just the slide background? So at a high level, these are the main image processing tasks in digital pathology. And so just to recap, segmentation, measurement, classification, and then of course, aggregating the details so that you have an overall sense of the data. Those are the main per image tasks, as well as labeling images in order to train a deep learning network or other machine learning algorithm. Okay, so let's dive into some of the challenges. And given that you're here, this is probably not much of a surprise, but these images are large, and large in this space is typically on the order of 100,000 by 100,000 RGB image, right? So in the case that's listed here of this TIFF image, it's 23 gigabytes of data, which is not nearly as large as what Russ was talking about, but when processed on an individual machine, it's large. You can always buy more RAM, but only up to a point, and swapping is painful. So as you get close to the limit of memory, systems grind to a halt. This is probably not a surprise. Let's look at just one region. You can see that there is the small block in red near my pointer. That collection of 240 by 240 pixels. That's about the size that a deep learning network for classification and segmentation is expecting to get. So obviously we couldn't pass this entire thing to the network, and these are just a small chunk of this data. When it comes to visualization, we can't obviously display this entire image because this overwhelms the video card RAM, which is even more limited than the RAM on a typical CPU system. Since the GPU uses the same RAM, it's a more constrained problem. So breaking the problem down into smaller parts is always involved in the solution. Okay, so processing images obviously involves the use of even more memory because you have the input image, you have the output image, and then anything that happens in the middle. Sometimes for images that are integers, like UN8 images, they have to be converted to a floating point type, which expands them out 4 to 8 times, whether you're doing something in single precision or double. And you can also make good algorithms and bad algorithms, and the choice that you make has an impact on the amount of memory that you use. So let's consider this simple equation, simple algorithm that masks out all of the pixels below 128, right? So we do a RGB to grayscale conversion, we do a simple thresholding. In MATLAB, this would produce a logical image. So ones where the values are greater than 128, zeros everywhere else. I'm going to make a composite output image to store the result so that the background is black and the foreground becomes the color of the original pixels. And I'm going to just assign those values into the output, right? So if I write it like this, 2 unneeded copies of the image are created. I have IM gray and mask, which aren't part of my result that I really care about, which is the IM composite, right? It's possible to reduce the memory utilization by combining the grayscale conversion and the thresholding into one operation, modifying the output in place if that's realistic. That can remove even more memory copies, right? So setting up the problem is an important part of the solution to using less memory. Another challenge is that the file formats often support multiple resolution levels of the data. So microscopes will frequently take real images at different resolution levels and then store them in the same file. Sometimes these have different origins and different coverage areas. And so it's important to note that finding the bytes to load from the file to get the same location in the image at different resolution levels is very non-trivial, because it's not as simple as just multiplying by a number and adding an offset. You have to keep track of where the origins are, as well as the resolution level, and then go into the file at the appropriate place. So this is error prone and tedious. And it varies by file format as well. File format authors generally haven't thought about large data. Russ mentioned FITS. It's a format that I helped support in the past, and it was definitely not made for very large data. A lot of these APIs were designed in the 70s and 80s when this simply wasn't a concern. Modern microscopy formats do take large imagery into account, but they're often hard to work with. Many of them are proprietary as well. So here's just one example of file format and showing some of its challenges. So it's a Apereo SVS. Basically it's a form of TIFF. It stores multiple sub-images within it. The first one is a full resolution tiled image. So it's the finest resolution that can be stored. And then the next one is not the next thing in the pyramid. It's actually a thumbnail of the entire image, right? And then the following images are within this file different pyramid levels that are also tiled. And then just to make things extra complicated, they took a picture of the slide label for identification and include that in the data as well. So this just goes to show that care has to be taken when understanding the data that's in a file. In microscopy and in digital pathology, knowing how big things are in real world units is really important. How big is a tissue region in millimeters or in microns? When you're pulling out a particular region, how do you correlate that spatial area with another spatial area? When storing information, typically it's stored with respect to the slide itself, and so we have to keep track of real world units. So I think this goes without saying that the challenges here are similar to the challenges that are seen in astronomy. It also works for other domains as well. If you turn the satellite around and look at the Earth, the remote sensing space has come up with many of these same issues and challenges. This is a GeoTIFF image that shows different resolutions at levels 1, 2, and 3 of the Boston area. All right, the good news is that these challenges are all solvable, and these are the main techniques that we have at our disposal for working with these large images possible. We can chunk it up. We can take that multi-resolution information, use it to our benefit. We can iterate through the data in parallel. We can do processing on only the data that we really care about, and we can work on multiple operations at the same time on the same pixel. I'll go into more of these in detail. Okay, so divide and conquer is the key technique for processing large images. Load less data and only when needed. I think we saw this in Russ's talk as well. If you abstract away the concept of a file and focus on blocks of data, it makes it possible to work with files interchangeably. So is it a TIFF file? Is it a file that's specific to a microscopy vendor? Abstract away the API with a facade to the data, and you have the ability to work with any file format. Just describe how to read and write portions of the file, and that's all that it takes. Many operations in image processing are pixel independent, or they only rely on a small neighborhood of pixels. For example, to do filtering, you only need the size of the kernel of pixels to handle each pixel. These can be handled independently on threads, multiple threads. A block orientation reduces the memory pressure at the expense of file access time, of course. So it's important to do as much work on each block of data in one shot as possible so that you only have to read the block once. Balancing the work that can be done on each block with the time that it takes to load that block is of course, one of the challenges and trade-offs that has to be tuned. Harnessing multiple resolution levels and loading blocks on demand to quickly visualize data and do some tasks using lower resolution images is another key technique to use. So if you can get by with identifying tissue at one level and then doing processing on that at the next, you pick the right level, I think. And that all leads into conditional processing. So for example, we want to find where the tissue is at the coarsest possible level. So this is an H&E stained image where the tissue shows up as either purple or pink, and the background is that gray color. We can easily identify the tissue regions by pulling way back, and then when we want to go and find the nuclei, we can limit ourselves to just the tissue areas and avoid looking in the background at all. So we'll be smart about where we do our expensive operation. So now that we know what are challenges and some of the techniques available, let's look at one framework for solving this large image problem. This is a relatively new framework that we wrote for MATLAB. The concepts can be implemented in any system that supports these same sets of features, though. We'll go through the framework and we'll use these tasks to motivate some of the features, all right? We've chosen to make an image the fundamental abstraction and not the file. Basically, anything that contains an image and metadata and also provides an API to load the data can be considered as an image. This includes web-based tiled image services, directories of chipped images, and so on. Even variables in memory can be used as a data source, and we've chosen to support all of those with our framework. Spatial referencing information isn't strictly necessary, but without it, resolution levels are assumed to cover the same physical space, have the same origins, and it's much more difficult to do anything with respect to real world units. So we'll use that information if it's available. And the result is, in MATLAB, it's called a blocked image, and you can see the result of doing it on one medium-sized image here. Has 3 resolution levels. You can see hidden in the sizes there are 3 different scales within this one TIFF image. And note that the 3rd dimension is 3. That's because these are RGB images. It also means that you have the ability to have differently sized blocks for each resolution level, and you'll actually see that here. The coarsest resolution level covers the entire image, and other ones are subsets of that data. The block size property uses a heuristic to upsize small I/O blocks. All right, and here's a visualization of that data. It's similar to what Russ showed you. We load the coarse image, and then as you zoom in, we on the fly load only the parts that are relevant for the viewport on demand. Okay, and by specifying world limits, as shown here by setting world start and world end, the data is put in physical units. This allows the regions to cover different spatial extents, like I mentioned earlier as well. So you can see that we have the real world measurements there in millimeters or microns, and we can use that with the functions to change those from world units to subscripts and vice versa. And so here's the results of running the commands on the previous slide. And note that these are the labels on the image are in real world units as well. Okay, the get region method reads contiguous pixels from different areas of the image. This framework supports arbitrary data dimensions such as 3D volumes and Z-stacks. But here the 3rd dimension is for the color channel. And notice that the same pixel indices return different regions of the image based on the resolution level. So that red box there in IML3 is actually IML1. So you can see that the same start and end locations are relative to the resolution level. And you use the sub to world and world to sub functions to convert between world units and the intrinsic pixel units. And then you can do this and call get region like we saw before if you have your locations in millimeters and then want to figure out where to look at a particular level. And you can see the difference in resolution there for the same spatial extent. It's worth noting that there's no reason that this has to be limited to 2D or 2D color data. We have extended this to 3D and ND data. This is a project that we had with the Idaho National Laboratory where they asked for help with segmenting out the zirconia granules in their CT scan of nuclear fuel rods in the 35 gigabyte volume. And here's this being used in our image labeling tool to label fluorescence 3D stacks of data. So this is technically a 4D volume. All right, so how do we do any image processing? Well, the apply function is the fundamental enabler for that. It breaks the images up into blocks of work, loads them on demand, processes them, and then stores the result in a new blocked image. And it supports parallel processing on different threads and conditional processing, and it takes care of extra pixels needed for neighborhood operations. So in MATLAB, FCN can be a function handle or an anonymous function. In another language, it could be a function pointer or any other kind of lambda or closure, right? And so the results can be images or data per block. So it could be an image or a histogram. It could be feature descriptors. It could be a text description. It could be anything. Normally, you'll want to pick blocks that are the same size as the tiling in the file, normally. Occasionally, you'll want to get power of 2 fractions or multiples of the tile size if they're unusually large or small. That way you can optimize for file access time and try to balance that with the amount of time that it takes to process the data in that amount of data. So you don't want to have a starved file IO pipeline, and you don't want to have a starved processing pipeline. And this is an example that shows what happens if you pick the wrong size of blocks. So notice there are 2 orders of magnitude difference in performance between the 32 by 32 blocks over there on the left-hand side and the native 512 by 512 block size. And most of that's because of repeated file IO calls. Even though we do some caching in the background in ours, it's just the extra bookkeeping and reloading that has to happen in order to get those blocks. And you'll also notice that as you use more threads, the data becomes increasingly IO bound because we're really doing kind of a simple operation here. A lot of care needs to be taken when using real data, that you use real data from neighboring blocks. The image here on the left shows what happens if you just do 0 padding for your kernel when doing a basic Gaussian filter. You get these black artifacts showing up, making this kind of checkerboard pattern inside the image. But if you take care and load data from the neighboring tiles, you'll actually use real data. So there's a little expense that you have to load neighborhoods, but that those get cached for reuse anyway. So it's probably not that impactful on the performance. These are the kinds of options that we have chosen to provide for doing image processing. These allow for multiple blocks to be used at the same time, multiple images to be used together. Other options change what happens on the boundaries or what you should do if there are incomplete blocks. Some of these are just helpful functions to let people know the progress of the data that's going on. Some of these operations can take hours, and it's always nice to give people a sense of how long things take and when they're almost done. So that works well for block independent or pixel independent operations. For more complex algorithms, we have the ability to get a block and then set a block of data. So this is important for things like flood fill or region growing, where you need to look at your neighbor and send data to them. So in this example, IM2 is a new blocked image with R and C columns. Unset blocks unset blocks have default values of 0. And so we're saying, here's how you define the image that you're going to put data into. Now go independently pull blocks, process them, and then set them into the output. All right, so far we've been implicitly assuming that there's a scheme, an iteration scheme used during operations like apply. And that scheme for us by default is to partition the image in a mathematical sense and then do sequential access. We formalize this pattern in MATLAB with something called a blocked image data store, where you don't need to know the number of blocks or where they are. You just keep calling read to get the next block of data and then process it and set it in the output. So this abstraction allows for splitting and shuffling, which enables parallelism and improved training of deep learning networks. And I'll talk more about that in just a second. So the tiling partition isn't the only way to operate on parts of an image. Sometimes you need random blocks of data, as with deep learning. Other times you need more data from some areas and less for others in order to do class balancing. So you'd want to feed roughly the same amount of background information and foreground information into an image. And as you can see here, there's different amounts of background and foreground. So you want to oversample some areas and undersample other types of blocks. And here's an example that shows how to select just non-overlapping blocks that have darker values, which, as I mentioned earlier, relates to the tissue and the histology image, right? So we're going to look for any value that's less than 170 is considered to be a foreground value, and everything else is background. We'll use that to make a mask, use that to set the block locations that we're going to use for our processing. And why would we do this? Well, this is the result of that previous operation. So if you look at the number of 256 by 256 blocks that contain just one foreground pixel and omit the rest, you've already limited the amount of processing that needs to be done by a factor of 2. Going up to just 20% of foreground pixels means that you've gotten rid of 3/4 of the processing time by not looking for nuclear or tissue information in the background of the image. So this is a trade-off, obviously, between how important all of the data is and how much you can leave to estimation. All right, and finally, I'll wrap up with this example that shows a concrete example of how this framework can be used in digital pathology. In 2018, researchers from Genentech worked with some of my colleagues at the MathWorks to train a UNet detector to segment large H&E stained images into 4 classes. So they broke the image down into training chips that they stored on disk, and then from them manually selected a representative balanced set for training. For inference, these images need to be broken into smaller files and then reassembled as well. And this is a natural thing that can be done with blocked image. The results of the UNet network were as good as those which were hand labeled by an expert pathologist, but the solution that they used before blocked image was cumbersome. So let's look at how the framework presented today can simplify this process. So with this new framework, each of the labeled images in the TIFF file is wrapped in a lightweight blocked image object. The balanced pixel labels function, that's just part of the computer vision toolbox, examines these objects, aggregates the details about the labels, and then creates a block location set object that can be used to create the data store that we looked at earlier, which yields blocks that tend to a uniform distribution of pixel labels. So there's no overrepresentation or underrepresentation of the classes. At this point, the UNet network training can happen in exactly the same manner as before, but without the need to manually chip or manage the files at all. So after training, the inference also uses blocked image. The semantic seg function, which is part of computer vision toolbox, takes those images along with the UNet network, calls predict, and within the apply method, which results in new blocked image instances, which can then be written back out to disk. So tiling images in this way is all taken care of internally, and people can really focus on a high-level construct of just the image that they want to partition and do prediction on. All right. So in summary, we have explored the challenges of working with large images in digital pathology, and we dove into the framework for solving those problems. By hopefully you've seen that by extracting away the difficult aspects, we're left with a high performance solution with pretty low cognitive overhead. You get to think about what's important to you, and that's probably what you want to do to an image and the image itself, and not any of that bookkeeping. And best of all, scaling from small image sizes for prototyping and large image sizes is seamless because it reuses the same functions. You just have to apply it to an in-memory image versus a blocked image. And with that, I really thank you for the opportunity to present today, and I'm glad that we finally had the chance to get this conference together. Thanks.
Thank you very much. So one of the questions I have actually for Russ, given what we're looking at here with the blocking, would this technology or technique be useful for analyzing the data that you were looking at earlier?
Yeah, it would. There's some work being done now on using convolutional neural networks to identify interesting features in these very large scale images. And those do need to block up the data set in a way that makes sense for training the CNN. So I think I found this blocking scheme to be somewhat interesting. I'm not sure it's directly applicable, but I think that it's something that could be the basis for an intelligent way to initially process the data to create the data sets for training. So yeah, it could very well.
Great. Got a question in the Q&A. Does the spatial referencing here allow for differences in orientation between the image and the real world coordinate systems? And parenthetically, they have in mind DICOM medical images where the patient coordinate system may be rotated with respect to the image. I think normal MATLAB spatial referencing does it do that, or does it not?
It does not. It assumes an XY that's spatially the same as the rows and columns. That's a fine question. I don't believe that the solution that we've described here today takes care of reorienting the data. There's fundamentally no reason that we couldn't apply to make some changes to this and have it work, to do the rescaling between XY and RC for rows and columns, of the data from world to intrinsic, as it were. Yeah.
Mm-hmm.